My name is Gary Pocock and this is my Week 10 reflection for the Modelling Instruction course. This week I'm going to have a close look at how energy is transmitted in electrical circuits. The reason I'm doing this is because on reflecting on the modelling notes, I felt that the energy story was not as clear and explicit as I would have liked it to be. So I thought I'd look into it into a bit more detail. And when I did, I had a very big surprise. Firstly, I found that the standard textbook stories left me with more questions than answers. And so when I looked a little bit deeper, I found that there is an alternative explanation for how energy is transmitted in an electrical circuit, which relies on the pointing vector. And this story is actually really surprising. So what I thought I'd do for this reflection is, first of all, do a survey of the typical explanations in standard first year textbooks for how energy is transmitted in a circuit. And then I would look at what is regarded as the correct model, current correct model, which is the pointing vector model. This could take a little while, so it may go over 2 reflections. Alright, energy in electrical circuits, how is it transmitted? First textbook I looked at was Giancoli's textbook, and here his paragraph describing how energy is transmitted. And this was my first surprise when I looked at all the textbooks. Discussions of energy in electrical circuits were very brief and very sketchy. Okay, so he provides a usual story that energy is transmitted via collisions between moving electrons and the fixed electrons in the wire. So according to this story, the electron transmits kinetic energy. The free electrons transmit kinetic energy to the atoms that they collide with in the wire, and this sets the atoms in the wire vibrating, increasing their thermal energy, which then gets transferred into heat and to light if you have a globe in the circuit. Okay, so comments on this explanation. Firstly, he doesn't invoke electrical fields at all. So he doesn't even use the term potential energy. He just says electric energy. He obviously means electrical potential energy. So in this story, it's stored in the electrons, whereas it is a much better explanation to say that potential energy is stored in the electrical field. And the second part of the story is that the electrical potential energy is first of all transformed into kinetic energy of the drift of the free electrons, and then it is transformed into thermal energy of the atoms in the wire. What do Resnick and Halliday say? Okay, so as an electron moves through a resistor, its kinetic energy remains constant. Okay, so we've got constant drift velocity, so kinetic energy remains constant. And it loses electric potential energy, which appears as thermal energy in the resistor. Okay, so this is a different story. First of all, no mention of fields again. So we have electrons themselves having electric potential energy. But because they recognize that the kinetic energy must remain constant, they are suggesting that the electric potential energy is transformed directly into thermal energy. They don't address the question of how the free electrons get kinetic energy in the first place. Presumably some of the electric potential energy is being transferred into electrons, but that's not discussed. Okay, what about Randall Knight's textbook? Alright, so Knight at least mentions the electric field. The electrons accelerate in the electric field and then collide with atoms in the lattice. Okay, so we've got electrons accelerating here. This is the first time he mentions that, because he has to, because he's referring to the field, and the field will cause electrons to accelerate. The acceleration phase is a transformation of potential to kinetic energy. Kinetic energy is then transferred to thermal energy. So Knight is trying to explain why the kinetic energy remains constant. In other words, why the drift velocity of the electrons is constant, and his suggestion is that potential energy is being converted into kinetic energy, which is then straight away being converted into thermal, or at least some of it is being converted into thermal energy, and this is being done in such a way that the kinetic energy remains constant as the electrons go round the circuit. Okay, so this is a little bit of a clearer picture. He at least mentions fields, and he tries to offer an explanation for how the the kinetic energy is constant around as the electrons move around the circuit. Finally, let's just look at Chabet and Sherwood's explanation. Okay, so the mobile electrons in the metal interact with the atoms in the metal, and they lose energy, which increases the thermal energy of the atoms. Okay, that's fine. Unless an electric field is present to increase the momentum of the electrons, the energy will be quickly dissipated and the current will stop. So here they're trying to explain how it is that the current continues and that the kinetic energy is constant, even though the electrons are losing energy in collisions. So this paragraph, very similar to Knight's explanation. Then on another page they say the following: we could discuss energy conservation by considering one electron as it makes a complete trip around the circuit. The energy gained by the electron as it is transported by the battery is dissipated in collisions as it travels around the wire. The funny thing about that paragraph is that they seem to have completely forgotten about fields, and we're now talking about an electron gaining potential energy, which shows just how easy it is to make a slip when you're writing a textbook. Then in paragraph 3 they get back to, which is on another page again, they're back on electric fields, and they provide an explanation that is consistent with the first paragraph. So in summary, it looks like textbook accounts of energy transfer are very vague, and they're not entirely consistent with each other. It appears, from what I can gather, that there is actually no underpinning mathematical model for any of these accounts. The most plausible account that I can extract from my brief survey, and I have looked at other books as well, but I thought these 4 texts pretty much summarized the various explanations of all the textbooks that I looked at. So the most plausible account I could extract from these was one in which electrical potential energy is stored in the electric field. This is converted into kinetic energy of the free electrons. The electrons transform this energy into thermal energy through collisions with atoms in the wire. But they maintain their constant kinetic energy by having potential energy continually transferred to them via the electric field. But as I noticed comparing Resnick and Halliday with Knight, Resnick and Halliday say that the potential energy goes straight to the thermal energy, whereas others suggest that the potential energy is converted into kinetic energy first. And I'm not clear how you would experimentally distinguish between those two models. Okay, so as I mentioned at the start, there is an alternative model, the Poynting vector model, and I've got a couple of papers that I will look at in a minute, or in my next reflection, that describe that model. But in those papers, they first of all offer some objections or criticisms of the standard textbook model. So I thought I'd just quickly look at those. So this is a paper by Sefton. It's an unpublished paper. Which was delivered at a workshop. And he has his objections listed before he then goes into the Poynting vector account. So his first objection is that electrons are just too slow to carry the energy fast enough to a light bulb. Okay, so he's reflecting here on the drift velocity of the electrons. And that is true. My response is that's a problem if you are not invoking electric fields to explain where the potential energy is stored. But if you are invoking electric fields, then you can explain on this model how the light bulb lights up immediately. The field transmits potential energy to the electrons all along the wire at the speed of light. So electrons in the bulb itself, when you turn the circuit on, will gain kinetic energy almost immediately. So this is not an objection that would apply to a field account. And Sefton lists other objections, but they're all the same. They all apply to non-field accounts, and I don't think that they work against field accounts. Another paper that I have lists various objections at the start of it. This paper is called Visualizing Poynting Vector Energy Flows in an Electrical Circuit, and at the start of the paper they list a series of objections to the standard textbook presentation. And I've picked out the first one because it's slightly different to Sefton's. On this objection, they say the drift velocities of charge carriers is constant throughout a single loop circuit, so energy cannot be carried in the kinetic energy of the charges. Well, again, that may be true for non-field accounts, but if you're invoking a electric field, then I don't think that holds. And it may not even be true for non-field accounts. What I wanted to say there was that in the case of Randall Knight's account, he has energy flowing, potential energy being converted into kinetic energy, but then converting into thermal energy. So this objection would not apply to his model. My final objection comes from another paper that I'll be looking at, which is also discuss the Poynting vector model. Their objection is not specific, but it's simply saying that the standard textbook's explanations do not provide a specific account of the microscopic behavior of circuits, which is absolutely true. So in my next reflection, I will look at the Poynting vector model.